Hey everyone, welcome back for another deep dive. Today, we're going to be looking at something pretty cool. It's a potential game changer in the world of displays. Positive feedback OLEDs. So you probably know OLEDs from your phone or maybe a fancy TV, but some new research that was just published in Nature Photonics takes things to a whole new level. These OLEDs are doing some pretty crazy things, like being both on and off at the same voltage, or even holding an image after you cut the power. It's wild. I've got our expert here to help us break it all down.
Thanks for having me. Yeah, it really is some fascinating stuff. We could be looking at a big leap forward in display technology, and maybe even beyond displays.
Okay, so before we get to the really mind-bending stuff, let's start with the basics. Can you remind me how regular OLEDs work? I know they use electricity to create light, but how does that actually happen?
Sure. So in a typical OLED, you have an organic material that is sandwiched between two electrodes. And when you apply a voltage across the electrodes, you're basically pushing electrons into this organic layer, and you're creating what are called holes, which are just spaces where electrons should be. When an electron and a hole meet up, they recombine, and that releases energy as light.
So it's like a little reunion, where they give off a burst of light when they meet up again.
Exactly.
Yeah.
And the color of the light that's emitted depends on the specific organic material that you use.
That's really cool. So what makes these positive feedback OLEDs different? What's the secret sauce?
Well, the key innovation here is that researchers have integrated what's called an organic photodiode, or OPD for short. They integrated this OPD with a multi-stack tandem OLED. The OPD is essentially a light detector. It absorbs light and converts it into an electrical current. And the tandem OLED, that's a special kind of OLED that is designed to be really efficient at emitting light. It's made up of multiple layers that are stacked on top of each other, and each layer can emit light, so you get more photons out for each electron that goes in.
Oh, so you're saying you're basically getting a bonus burst of light with this tandem OLED.
That's one way to put it, and this is where the positive feedback comes in. Some of the light that's emitted by the tandem OLED, it gets reabsorbed by the OPD, which then generates more current. And that extra current then drives the OLED to emit even more light. So it creates this kind of self-amplifying loop where the light kind of feeds itself and gets stronger.
Wow, that's incredible. So the light's kind of like a plant watering itself.
Yeah.
And growing bigger. But hold on, I thought you couldn't get more energy out than you put in.
Right, that's a fundamental law of physics. And we're not breaking any laws here. The extra energy isn't coming from nowhere. It's coming from the electrical power that's driving the device. Think of it like a microphone and a speaker. The microphone picks up a faint sound and converts it into an electrical signal. The speaker then uses that signal and some external power to amplify the sound, and that makes it much louder.
Okay, I see. So it's not creating energy, it's amplifying it. And what's really cool here is that it's using light to do the amplifying.
Right.
That's what makes this so different from how traditional electronics work.
Exactly. This is a great example of what's called optoelectronic upconversion,
Yeah.
where you're taking near-infrared light, which we can't see, and you're converting it into visible light.
So this feedback loop is what makes these OLEDs so special. But what does that actually look like in practice? How does this light amplification actually manifest itself?
Well, one of the most striking effects is what's called a hysteresis loop. Now, that's kind of a technical term. But what it basically means is that these OLEDs can have two different brightness levels at the same voltage. It depends on whether you're increasing the voltage or decreasing the voltage.
Okay, I'm going to need you to break that down for me a little bit.
Yeah.
I'm picturing a dimmer switch where you smoothly adjust the brightness by turning a knob. So how is that different in these positive feedback OLEDs?
Okay, so imagine you have that dimmer switch. As you turn it up, the light gets brighter, just like you'd expect. But with these OLEDs, when you start turning the knob back down, the light stays bright for a while, even though you're lowering the voltage. It's kind of like the light switch gets stuck in the on-in position, even though you're trying to turn it off.
Yeah.
And then at a certain point, the brightness suddenly drops, like the switch finally flipped.
Wow. So it's almost like the OLED has a memory of its previous state. That's definitely not how my regular light switches work.
Yeah, that's a great analogy. And that unusual behavior is directly related to that positive feedback loop. It's that self-amplifying effect that creates a kind of inertia in the system. Once the OLED is in that high brightness state, it takes a significant change in voltage to get it to switch back down to the low brightness state.
That's so weird and so cool. But why is this hysteresis loop such a big deal? Is it just a scientific curiosity? Or does it actually have practical implications?
Oh, it definitely has some huge practical implications. This unique behavior opens up a whole world of possibilities for displays, sensors, even computing.
Okay, now you've got me hooked. Tell me more. What kind of possibility?
Well, imagine a display that could hold an image even after the power is turned off.
Like a Kindle, but way more responsive. That would be awesome.
Exactly. So this hysteresis effect could lead to displays that only need power when they're actually changing the image, not to just maintain it. That could mean massive energy savings, especially for things like e-readers or digital signage.
That's incredible. So you're saying you could read an entire book on a single charge? Because the screen wouldn't need to be constantly using power to stay lit.
That's the idea. And it goes beyond displays, too. These devices are also incredibly sensitive to light. So that opens up some really interesting possibilities in what's called upconversion imaging.
Upconversion imaging. Okay, that sounds kind of sci-fi. What are we talking about here?
Well, remember how these devices take in near-infrared light, which is invisible to us, and they convert it into visible light. That means we could use them to see things that are normally hidden from our eyes.
Oh, wow. Like a superpower. But how would that work in the real world? What are some examples?
Okay, well, let's take medical imaging. Imagine doctors being able to see through tissue and get a clear picture of what's happening inside the body without having to rely on x-rays. Or think about night vision goggles that don't need bulky batteries, and they don't emit any detectable infrared light, so they'd be much more covert.
That's incredible. Being able to see things that are usually invisible. That's straight out of a comic book.
But wait, we were talking about computers earlier too. How do OLEDs fit into that picture?
Ah, yes. So this technology could also be a game changer for what's called neuromorphic computing.
Neuromorphic computing, is that like computers that can think like humans?
Well, it's not exactly about making computers think exactly like humans. It's more about mimicking the way that the human brain processes information. Neuromorphic computing is all about trying to create systems that are inspired by the structure and function of the brain. And these positive feedback OLEDs, they can actually act as artificial neurons, processing information using light instead of electricity.
So we're talking about light-powered brains. That's pretty wild. It all sounds amazing. But is any of this actually possible? What are the challenges here? Are there any hurdles we need to overcome before we see this tech in our everyday lives? Well, as with any cutting-edge technology, there are always challenges to overcome. One of the biggest hurdles with these devices is that they're very sensitive to defects, even tiny imperfections in the materials. Those can trigger the positive feedback loop prematurely, and that can lead to unpredictable behavior.
So it's like a delicate balancing act, where one tiny flaw can throw the whole system off.
Exactly. So researchers need to find ways to eliminate those defects during the manufacturing process if they want to ensure reliable performance. And there's another challenge, too. We also need to improve the efficiency of OLEDs when they're operating at very low currents.
Oh, really? I thought these devices were all about amplifying light. Why does efficiency at low currents even matter?
That's a great question. So there's always some energy loss in any system, right? And right now, OLEDs aren't very efficient at converting electricity to light when they're running at those very low currents. And that inefficiency can actually make it harder for the positive feedback loop to get going.
Ah, so it's like having a powerful engine, but a leaky fuel line. You're losing some of that power before it can actually do its job.
That's a perfect analogy.
Yeah.
So improving that low current efficiency, that's going to be crucial to making these devices even more sensitive and efficient. It'll unlock their full potential.
So are scientists actively working on these challenges right now?
Absolutely. This is a very hot area of research. Scientists are exploring all sorts of different materials and fabrication techniques, trying to address both the defect issue and the low current efficiency problem.
It's exciting to think that we could be on the verge of a major breakthrough in OLED technology. So what does all this mean for the future? What are the long-term implications of this research?
Well, it's hard to say for sure.
Yeah.
But the potential here is really remarkable. I mean, we could be looking at a future where displays are incredibly energy efficient, medical imaging takes a giant leap forward, and computers start to function more like the human brain.
It's amazing to think that just this one seemingly small tweak, adding an OPD and using a tandem OLED, could lead to such massive changes.
Yeah, that's the beauty of scientific research sometimes. Sometimes a small change can unlock these incredible possibilities and open up these entirely new fields of exploration.
That's a great point. So for our listeners out there, what's the takeaway message here?
I think the big takeaway is that innovation often comes from unexpected places. This research shows us that even well-established technologies, like OLEDs, they still have secrets to reveal. So we should never stop questioning, never stop exploring, and never stop pushing the boundaries of what we think is possible.
That's a great reminder for all of us to stay curious. Well, that's all the time we have for today's deep dive into the fascinating world of positive feedback OLEDs. I don't know about you, but I'm definitely walking away with a sense of wonder and excitement about the future.
Me too. This is definitely a field to watch closely. Who knows what incredible breakthroughs are just around the corner.
A huge thanks to our expert for being here today, for sharing their knowledge and insights with us. And to all of our listeners out there, thank you as always for joining us on this journey of discovery. Keep those minds curious, and we'll catch you on our next deep dive.